All right, let's revise that we learned last week. So from last week we started module 8 and we learned about how to analyze qualitatively, basically. We haven't learned about quantitative analysis yet. We're only dealing with that, how qualitatively analyze such like organic compounds. So we started from this one here. So how do we, by using some chemical test to determine that organic compounds, we were able to determine the presence of the unsaturated carbon. Okay, without looking at anything here, guys, so I'm talking about something like alkane. Ian, how do we, doing any of the chemical tests, how do we determine the presence of the alkane? Alkane.
So you first do the bromine water test.
So, okay, bromine water. Very good. Bromine water test. So that's using the BR2, the liquid, or the aqueous. Most likely the aqueous, I'm sorry. Now, what do you expect for the bromine water test if we have some alkenes present in the sample?
Alkene. So when you mix it, the color, the solution changes, becomes decolorized.
Okay, so it means it decolorizes the brown bromine water, bromine solution, if we have alkenes in it. Good. Anything else?
Acidified permanganate.
Okay, very good. We use the acidified permanganate. And what do you expect using this? Expectations.
Purple to
It'll be decolorized again too. Decolorize the purple in the presence of the alkenes there. Very good. Okay, show me you're good. All right. Then, how do we test for? This is for the unsaturated carbon. How did we test for the carboxylic acid?
something carbonate.
Something carbonate.
Sodium carbonate.
Sodium carbonate. So we use a sodium carbonate. Anything else? We either use sodium carbonate.
pH test.
Sodium carbonate solid. Okay. Are we using the solid powdered sodium carbonate or the solution? We actually use a solution.
So in the homework, there's something about powdered.
We could use the powdered, but you generally use the solution because it has a lower concentration. It's actually safer because the reaction between carboxylic acid and carbonate would be exothermic too. So, and I can also use a sodium bicarbonate aqueous or the solution too. And what do you expect? Expectation from here.
H2 gas.
Or CO2 gas.
Okay, the CO2 gas produced. And how do we test for the CO2 gas? We can test with the lime. We can confirm with the lime water test. Now, lime water is good to know. It's made with the calcium hydroxide. That's a lime water. So what happens is when the calcium hydroxide react with the carbon dioxide, they form the precipitate of the calcium carbonate. Okay, we had one question in HSC last year, so it's good to know the calcium hydroxide. Good. Anything else for the carboxylic acid? pH test. Good. We can use the pH test. What do you expect with the pH test for the carboxylic acid? Bar. Which is, so that's using the litmus. BAR, blue litmus paper turns to the red. Or the pH level must be lower than 7. But that also depends on the concentration, as we learned from the acid and base module 6. Okay. Now, third. We also learned about how to identify alcohols. Jeremy, how do we identify the presence of the alcohols?
You can use permanganate solution H plus /
Before that, I just want to know there's alcohol. I just want the
sodium metal.
sodium metal. Okay, we use sodium metal test. And what do you expect?
Hydrogen.
There will be a hydrogen gas produced. And how do we confirm the hydrogen gas? Bubbling, yeah. We call that pop test. We do the pop test to confirm that this is the presence of the hydrogen gas. Good. Okay. Very good. Then how do we distinguish the whether there will be a primary, secondary, or tertiary alcohols?
If it's permanganate, you can kind of already differentiate. You can if it react with the
KR2.
Okay, so we can either, okay, let's write it right here. Primary, secondary, and tertiary. We can use the agent of the acidified dichromate,
CR2.
okay, or either use acidified permanganate, or
Better to use zinc chloride.
we can also use the zinc HCl with the zinc chloride. That's substitution reaction. So let's go for each. If we use permanganate there, yes, it's good to use the zinc chloride in there too.
Identify each one.
Yes, it will do, but it's sometimes we don't have that, or we just want to confirm that using this is a more rapid reaction. Because as we learned, zinc chloride, let's start from zinc chloride then. The primary alcohol would not have any reaction with the zinc chloride, so no reaction at all. Okay, the secondary alcohol would be slow reaction. It takes about an hour. This is why sometimes we prefer using the oxidizing agent rather than this one. And what do you expect as a part of the reaction?
like a layer.
There will be layers formed. Some sort of precipitate, and due to that immiscible property here. Tertiary alcohol will be really fast reaction with the zinc chloride and hydrochloric acid. Okay, what about the primary alcohol with the dichromate? What will be the color change you expect?
Orange to green.
Orange to green. So we will expect to see the green for the primary when we have the primary for the zinc for the dichromate. Secondary, it'll be the green as well. Now tertiary would it be remain as orange or yellow, or kind of orange, orange, yellow, yellowish orange, depends on the concentration. Permanganate. If we put the permanganate, it'll be colorless. It'll be colorless for secondary alcohol, and tertiary alcohol would be the purple. Here's the purple color. Very good. So these are the three types, the functional groups. Okay, let's talk about then amines. It's not part of the syllabus. It's not part of the workbook. So how are we going to identify the presence of the amines? Then amines is something R with the CH.
You can do similar thing with amines, which you did to alcohol.
Like how? Which one? Which agent we're going to use?
Like you can use the zinc chloride.
Can we? Yeah. And then what do you expect? Slow reaction. Or we can think about the amines. Guys, think about the amine. Amines working as a weak base. So if this is working with some weak acid, some carboxylic acid, so reaction with the carboxylic acid. And what do you expect from there is substitution reaction, so that NH2 will be released. There will be a release of the ammonia gas. And how do we test for the ammonia gas? Ammonia gas, we can use the litmus paper.
Can you also do
Gas. If the gas is coming out, putting the litmus paper or the red litmus paper, if that turns to the blue, it shows that there's a ammonia gas presented. We can actually smell that strong smell, odor of the ammonia too, but that's more exact. Yes, John.
like acidified potassium permanganate?
We can also use acidified. And what do you expect?
It's going to be neutralization.
It's oxidizing, so I don't think NH2 would prefer to be oxidized.
Like with
amines, the oxidation of amines.
Yeah.
Is that, amines can be oxidized?
Can't amine, like, I don't know, acidified potassium.
Is it written there?
No, I just read it on something that like, when you know, like adding potassium permanganate, like it's not limited to just alcohols, but to like aldehydes and like amines.
Yeah, but we haven't learned about the oxidation of amines, so don't worry about that for now. Okay, just quick chemical tests to determine each of the functional groups here. Okay, any questions? Then we learned about this IR, infrared. Dongyu, how would you describe the function of the infrared spectroscopy? Yeah. Infrared spectroscopy.
Like how it works?
Yeah. well, like I ask you to like memorize it, but like just briefly, I explained you with some example.
Is the vibration between
Vibration between, so it depends on the bond, what kind of bonds, the kind of bond strengths, bond lengths they have. The vibration of that would be. No, that's the mass. Okay,
you need
the
to know the equipment used,
for the IR.
like for the mass spectrum.
Mass spectrometry, yes, definitely for that one.
The,
For the IR, it would be half and half. Like NMR, which we're going to learn today, you need to know that. IR is quite not there yet. Okay, so IR, as you said, like when like atoms or elements or compounds receive some energy, they get vibrate. They vibrate it, and depends on the length of that bonds they have. Okay, they have a very specific vibration formed, which can be detected as a forms of the infrared, which is EM wave in here, electromagnetic waves. So we talked about the various functional groups in the IR here. Do you remember I asked you to memorize the shape of each? So shall we go through each over here? How do we know there's a carboxylic acid present?
Like 1,700. It's like a massive dip.
Yeah, 1,700 too.
1,000.
So there will be strong and narrow signal at
Around 1,700.
1680 to 1750, which indicates what? No, that indicates carbonyl.
Yeah.
A functional group here. What else?
OH.
Yeah, OH. How do you know it's the OH?
strong and broad.
Strong and very broad. At around 2,500 to 3,000. That indicates that OH, which is an acid. So it'll be looking like this, something like we have very broad and some signals here
Why
from
do they
here.
give us like CH bonds?
Because there will always be the CH bonds, because they will, yeah. Because by just looking at CH, because every organic compound has CH, it's impossible to determine the functional group from it, unless we have alkane or alkane. Yes, Ian?
The CO bond important. Is CO bond important?
Which is CO bond. Carbon and oxygen, the single bond oxygen. That varies, again, that varies. Because that can be like, it's hard to describe this carbon single bonded oxygen, because that can be sometimes narrow and strong, sometimes be medium too, which is not so definite. But if you're definite, if you're sure, if you definitely know about the functional group, you can relate that. But if you don't have any ideas about the functional group yet, I don't recommend to use it. All right. Jeremy, how do we identify the presence of the alcohol in the IR?
It's the two. It's like a wide opening bar.
Hmm?
It's like this,
Same.
Like the W shape.
Yeah.
No W shape. Oh, yeah, kind of W
Is it
shape.
not a W shape?
Slightly, but I wouldn't say the W shape,
Strong, very good.
because that's a mix of the CH and the alcohol. So strong,
Very good.
how do you describe it? Strong and it'll be broad. Okay, show the difference between carboxylic acid. Carboxylic acid will be really broad as this. Alcohol would be something like that, kind of W shape. Bit of like, no, there's a kind of broken peak that I described that here. Strong and broad signals at where? 3,230 to 3,550. That's indicated that OH, which is the alcohol. Anything else for the alcohol? Anything else?
Carbonyl.
Yeah, okay. What about for A mines? The presence of the A mines.
Teeth shape.
It would be like a tooth, like a shape, or I would call it W shaped. Could it be a strong? Could be broad. Could be
Short.
it's a bit short. It depends on like what kind of A mines you have. So that's more the definite kind of structures at around where
3,000.
3,300 to 3,500. Okay, that shows the amine structures. What about amides?
Near carbon.
Yeah, amines have, the only difference between amines and amine is this one has carbonyl, which is COO bond. This, it doesn't have one. So both of them will have the tooth shape or the W shape, but for amines only, it will have the strong and the narrow at 1680 to 1750. That's representing carbonyl. That's for the amides only. Are you guys writing this down anyway?
Do you need?
Well, like, it's up to you. I'm giving you a summary of the whole thing as last week.
Did you write this down?
Yeah, like if you have one, then you can use that. That's indicating the N and H bonds.
You can't tell aldehyde and ketones, right? Like it's hard to, right?
No, no. So I would put the same group of the aldehyde, ketone, and the ester.
We're gonna know. We're gonna learn how to.
Oh, not from the IR though. So what do you expect? Tell me, what do you expect if you have any of these in the IR?
And strong at 1,680 to
Yeah.
1,750.
Let's do that. So we're gonna definitely have the strong and narrow signals at 1680 to 1750. That's indicating that. Anything else? How do we ensure that that's the aldehyde, ketone, or the ester? Absence of absence of the OH at 3000. Well, absence of any other signals too. Or like you can just say there will be like just the carbon and hydrogen, like the signals there. Yeah.
Does the bramine test also work for alkenes?
Alkynes, you mean? Alkynes, yeah, we will work with alkynes too. But we don't have the alkynes in the liquefied, like or aqueous form more. So most likely be the alkenes. Do you have any questions?
Do we have like two different things?
Yeah, but whether we have this alcohol or that, they're region of the 3000s around.
Question, it just like in the homework question, it just required us to write OH and the like value. Like, I wasn't sure if it was like requiring for the alcohol or the like acid. Maybe the last question of the homework.
Yeah. The absence of that.
In the like texture thing. Does it provide the wave number of OH? And
Yeah.
it didn't show if it was like acid form or alcohol.
That all depends.
I just went for like alcohol because it looks like
The last question? What question?
like in the textbook, page 155.
Yeah, what about it?
It says bond OH and wave
Yeah.
number.
Don't you look at the shape?
Yeah, that's why
The
I-
1 and 2, are these the same?
No, because that's why I just wrote alcohol.
Which is alcohol?
Yeah, it is, but
The first is alcohol, second is carboxylic acid.
are you meant to look down?
What do you mean look down?
Because in question A, you just get the table and that's it.
Yeah, you'll use your data sheet. Use your data sheet. You give me that.
You meant to write both,
Hmm?
like both values in the data sheet, or just the alcohol.
You have both data and data
Yeah,
sheet.
but in the answer, you meant to write both or just the alcohol value.
Just write the both. Write the both, yeah. Okay. Alkanes and alkenes. Oh, check your answer. Okay. Check. I posted the answer for that too. To see how they're wrote in there. How do you know there's alkanes and alkenes only? So this is what I showed you from your sample A, B, C, D. You have to compare the sample A, B to the C, D. So alkanes, both of them would have the very strong. It's kind of narrow. Signals at that's gonna be broad because CH4 would be like 2,850 to 3,300. It would be really broad. But for the alkanes, what you have to remember is the signal would be something like really long peak, as given over here for the others for the alkane. For the alkanes, however, you will see some fragments like this. That's for the alkane. but the position of the signal will be different, vary by what kind of alkanes we have too. So this is why I kind of broad generally write the broad range of the alkane signals and alkene signals. But look at the shape. Shape is very important. I didn't really ask you to memorize anything here. I only ask you to memorize the shape of each of the functional group. That's all you need to do. Okay, don't ask me or don't question that why the shape is like that. If you want to learn that, study in university. You will get in details there. All right, that's for the IR. That's the information we can get. So let's talk about pros and cons of using the IR. Dongyeon, what would be the pros and cons of using the IR spectroscopy?
Can clearly identify the functional groups.
Okay, the pros. It's not like 100%, but it depends on the carboxylic acid case. Yes, kind of definite. Alkyl definite. Amide, yeah, definite. So it will give us a clear picture of the functional group.
Maybe the bonding properties.
Not really. It's hard to tell. Like more on the carbonyls. Cons.
I don't know
Which
which one.
one? What? Which one?
Ethane or ethane.
Yeah. So you is unable to get the specific or the molecular structure. So by looking at this shape here, we don't know that whether that would be a butane or propane or something else too. This is impossible from the IR unless we learned about fingerprint regions, but you don't need to touch that region at all. Okay, that's for the IR sections. Any questions about IR? Everyone good? Okay. Then we also learned about mass spectrometry too. Okay, John, tell me about mass spectrometry.
The steps.
Yeah. What are the steps for the mass spectrometry?
Vaporization.
So vaporization, okay.
Yeah. So you vaporize it until it's like all evaporated.
All like in the gaseous state, very good. And then?
And then
I,
Yes.
which stands for something related to chemistry, known as ionization. Okay, and then A, which is acceleration, and D, deflection, and D, detection. So via DD. Okay, via D, or via DD, whatever. Just memorize the via DD. Okay, so each of that, it's a step to the, how we use the mass spectrometry. Vaporization, as John explained, yes, you're vaporizing. Put a sample of the organic compound in the machines. Basically, they're heated up to make them to be all vaporized so that they can easily get targeted. The reason for the vaporization is you can think about you are kind of separating one molecule to another molecule. So each of them can be easily get targeted by energized electrons. Ionizations, we use that. We use the strong energized electron, okay, to making the fragmentized. We're kind of cutting the bond between carbon and carbon mainly. Sometimes getting the bond between carbon and oxygen, depends. Acceleration, Dongyeon, what do we use for the acceleration again? Which is, come on, metal plate doesn't do anything. It needs to be connected to something. Yeah, electric field, E field. Electric field is used to accelerate that. Jeremy, what do we use for the deflection? Deflection. Remember that we use a magnetic field or B field. Okay, I only ask the question to those who are doing physics because you learned that charged particle in the B field. Remember that. Detection, use the computer. So basically, you count the quantity each of the fragments too, so that we get something look like here. So let's go straight to the information that we can get from the mass spectroscopy. Okay, show me what kind of information can we get from mass spectroscopy?
Molar mass.
We can get the molar mass. So molar mass from where?
The largest peak.
The right hand side. So if I pick like this,
Highest MZ.
no, we see like this is MZ. That's known as the molecular ion peak, sometimes known as parent molecular ion peak. The very last peak, right on the right hand side, using the molecular ion peak, we can find the molar mass of the compound. Okay, anything else? Any other information can we get from this mass spectrometry? From the base peak, okay? From the base peak, what kind of information can we get? Something density. We can find out about the possible structure, okay, or possible fragments, or from the fragments of the compound, we can determine that it's a possible bonding structure. Because, as I said before, yes, when the carbon is connected to something electronegative, it gets the partially positive, which means that the partially positive carbon is easily get targeted by super energized electron, which is negatively charged. So that the bonds of that partially positive carbon will be targeted. From there, we can get the base peak. So base peak means that the most abundant the fragments from that segments of the compound too. It's kind of giving us the idea that, yeah, possibly we can have some partial polar carbon bonds present in there. In case we don't have any partial positive, there's a case, the base peak, so that's called the base peak. The tallest peak is the base peak. The base peak can also be the molecular ion peak in some occasions. So which means we get something like the base peak is the molecular ion peak, and we get some other fragments like this. Oh. It's possible because when we have the fragments, the carbon is not really partially positively charged there too. That means the whole things get to just be ionized, and we can detect them. There's some occasions we can have that. Okay. Why do we have that little fragments like this? Like if you see that before, or some of this.
Carbon 13, carbon 14.
Good. Carbon 13, no, not carbon 14, carbon 13 and hydrogen 2. Isotopes. Isotopic effect, which means that you have a plus minus 1, okay, or plus minus 1 to 2. Having that little small fragments next to the peak, because some of the compounds would carry the carbon 13 or hydrogen 2 isotope, so therefore they're having a more extra 1 or 2 the mass number. If we have a halogens, by the way, remember that chlorine, bromines, they have more isotopes percentage here. So remember, for the bromine, for example, they have a very 50-50 so you actually see the very similar the peak length or peak height for the bromine, the number, the 2 isotopes of bromines. Same for the chlorides, we got to follow that, the percentage of the isotopes. Okay, so that's a possible information we can get from the mass spectrometry, infrared spectroscopy. That's something we learned last week. Any questions about the last week's one? So think about what information you can get. Mainly, we get the information about molar mass from the mass spectroscopy or mass spectrometry, and infrared spectroscopy we use that functional group. So combining these two, we're somehow getting some picture of the possible unknown compound. We don't know what the compound is, so you're going to do a chemical test. You do the chemical test, you put it onto the IR, you put it onto that. So that we'll get next week. Any questions up to here?
What does that say? Next acceleration E dash.
Oh, E field. Electric field and the magnetic field. So the new tools known as the NMR stands for nuclear magnetic resonance spectroscopy here. So NMR is a new tool that we're going to learn. So NMR spectroscopy. NMR stands for the nuclear magnetic resonance.
Is this also a physics?
No, some. It's actually working very similar as MRI machine, magnetic resonance imaging. So, but it's part of the physics, like before we change the syllabus, but you don't have to know. Okay, I make it really easy to explain in here. So what I have, so this is like what? This is, I have some methyl kind of alcohol given over here. Okay, black for the carbon, white for the hydrogen, red for the oxygen. Now, when I put that in this, collect the sample, okay, and what I do is I put something really strong magnetic fields on here. Then, because some of these carrying some positive and negative there, the magnetic field from external magnetic field from this positive and negative charge make this to be spin like this. Yeah, it's actually making spin, making like spinning. And depends on spinning, like think about here. The bonding between oxygen and carbon and oxygen to hydrogen are quite different. What I mean is, because oxygen has a very specific electronegativity, pulling the electrons to here, it would have it really bonded to the carbon really strongly. Or the carbon will be more stronger than in here, because this is non-polar bondings, there's a kind of partial charge bondings here. What makes them is, due to that positivity or due to the bond strengths, the spinning of each of these would be quite distinctive. You can imagine that if someone's holding you really tight, it's hard to make a spin or self-rotate. You can self-rotate easily when you're freely moving around. But when someone's holding your back or your clothes like this really tight, you can't really spin a lot in here. So the way we can detect the signal is when something's completely make the spinning, they produce something called a radio wave. We kind of capture the radio wave, the kind of wave, and get the signals of that too. This is how the NMR is functioning, which means different functional group, different bondings would have the very specific, the signals will be detected here. So for the NMR, we have two types of the NMRs. One is NMR using the carbon-13, which is using the carbon-13 NMR. Second is we're using the hydrogen NMR. That's also known as proton NMR. So you can just think that carbon-13 is we are spinning the carbon. We're basically spinning the carbons. So yeah, carbon as in like these carbons here. We make these carbon to spin like this. Okay, so that we can detect what's going on in here. HNMR, proton NMR, basically we're spinning this this hydrogen. We make them spin using the magnetic field. So to understand how the signals can be different here, we have to know about what gives them the different signals in that case. Depends on what carbon is attached to next in here. They will definitely have a different spinning process. Okay, for example, when look at this carbon here. This carbon is attached to this oxygen. Means that oxygen is really strong. It's kind of holding its back. So for this carbon, it's hard to rotate. It's heavy. It's more like hard to rotate freely compared to these carbons here. They are free to rotate around. For this carbon here, because it's bonded to the oxygen, it's really hard to rotate around in here. Same for the hydrogen attached in here. You can imagine that hydrogen attached to the oxygen would be hard to rotate because it's really strong. However, for the hydrogens attached to this carbon, they'll be freely rotated around in here. This is kind of easiest way to understand about NMR, okay? And it actually requires some physics to understand it further. But you don't need that for chemistry. So where do we use that? So to understand the NMR, we have to start with something called as a chemical environment. This is also on your page 162. So I'm going to show like one thing here. I'm going to talk about chemical environment as environments. There are two types of environments. One is a carbon environment. And second is the proton environment, or proton or hydrogen environment. Show you one example. I have it's given here. Okay, I'm going to put that in red and blue differently here. This is ethane having 2 carbons here. So the number of the carbon we have is 2. So let's have a look at this carbon's environment. Environment as in like what does it have around it, surround it. So the red, as we can see from here, the red carbon has 3 hydrogens attached. Three hydrogens attached. Okay, and the next to here, what is attached? There's a CH3 is also be attached. Okay, that's for this carbon, red carbon's environment. Can you understand the point here, Jeremy? Do you understand the point? Like there's 3 hydrogens attached and CH3 is attached for this carbon's environment. What about blues? The blue also has 3 hydrogens attached. Okay, and on the left hand side there's a CH3 is attached too. So by comparing that these two carbon, the red and blue's carbon environments, can we say they are actually having same carbon environment in here? Okay, so in that reason I will say, oh, there's only one carbon environment. The fact is, the carbon environment doesn't say the number of the carbon. It actually says that what carbon kind of environment, the neighborhood, kind of what neighbors they're having. So as we can see from here, the way we can find that is these two are actually what? Symmetrical. They're symmetrical. So when they're symmetrical, we can say they have the same environment in this case. Okay, let's talk about the hydrogen then. Hydrogen. Look at this, the red hydrogens and blue hydrogens. Okay, John, what can you explain about? How can you explain like this red hydrogen's environment? Think about like what the hydrogen environment is.
Just attached to the carbon.
It's attached to the carbon. I mean, every hydrogen must be attached to carbon, but look at the neighborhood. So it has. So look at the next door, just next door. I don't really interest like there are probably they are living with 2 hydrogen living next to, but there are 3 hydrogens living next door. Can we say, okay, from this red hydrogen's perspective, or any of these red hydrogens perspective here, okay, we can say, hey, there are 3 hydrogens living next door. The 3 hydrogen here. Does it make sense to you? I'm just using the living next or neighborhood. Just living. You look at the you can just say carbon as the house, okay, and think about these are the tenants. These are the people living in there. So in the next door, there are 3 hydrogen living in there. What about for the blue? Same. It will be the same. There will be 3 hydrogens living next door too. So are they the same environment? Yes, we can now say they are the same hydrogen environment. So therefore, there will be 1 hydrogen environment as well. Okay. Use the second example you have. We have now propane. This is propane. I'm gonna put that in some blue, red, and the purple. Jeremy, can you explain, describe this blue carbon's environment?
He has 3 hydrogen attached.
Yeah, it has 3 hydrogens attached and
CH2.
it's a CH2 living next door.
Yeah.
Good. So you can describe that as, hey, this carbon has the 3 hydrogens living together, and the next door there's a CH2 living next door. Okay, what about for purple? It would be the same. Purple has 3 hydrogen living in that carbon, okay, with the CH2 living next door. So can we say this blue and purple carbon has they have a same carbon environment? Does it make sense here? So there'll be 2 carbon environments. What about the red? Jongmin, how would you describe the red carbon's environment?
2 hydrogens
There are 2 hydrogen living inside and
attached to 3 methyl.
3 methyl,
3 carbon.
3 2 carbons. Is that just the carbons?
Methyl.
No, methyl, yeah. So can we describe that as this red carbon has 2 hydrogens living inside with 2 CH3s each on the left and right. On the neighborhood, there are 2 CH3 living next door. Oh, it doesn't have to be left and right because it'll be like tetrahedral shape, by the way, here. Doesn't really matter. I just would say that in the neighborhood next door, there are CH3 and CH3 living. So this is different to this carbon environment definitely here. Yeah? So there are 2 carbon environment. One is 1 and 2 is a 2 separate carbon environment. You all right?
No.
Okay.
Can you explain carbon environment again?
Carbon environment. Look at what this carbon's with.
Yeah.
Tell me. This blue carbon.
3 hydrogens.
They're living with 3 hydrogens and the next door,
CH2.
1 CH2 next door.
Yeah.
What about this purple hydrogen?
Same thing.
Same thing. So can we say these 2 have a same environment?
Yeah.
Yeah.
But what about the one in the middle?
One in the middle. The red carbon has 2 hydrogens living inside
Yeah.
with the 2 CH3s next door.
So when you say 2 carbon environment, it's saying that each
The-
carbon has
2 carbon environment means like I'm just counting the number of the carbon environments we have in this compound.
so each carbon has 2 environments.
No. No, I'm just saying for this molecule here,
Yeah.
this molecule here, I have 1 carbon environment of the carbon with 3 hydrogen and 1 CH2. This is 1 carbon environment.
Yeah.
1 type. Okay, another carbon environment C1, C2 would be the 2 hydrogen living, and there are 2 CH3 in here. Yeah?
Oh, since that one is the same, it's 1 carbon environment.
Can you what?
It's a coffee.
Yeah?
Since that one is the same.
They're the same. Yeah,
it's
symmetric.
1 carbon because it's the same.
Yeah.
But this, since there's the CH2 in the middle,
Yeah.
it's 2.
So it's also symmetrical, isn't it? Okay. What about the hydrogen environments? John, how would you describe this one's hydrogen
I
environment?
think it's 1 carbon.
Okay, it's these three hydrogen would have the same environment, aren't they? So next door, next door,
is 2 hydrogen.
there's 2 hydrogen living next door. Okay, what about this one? Same. These 3 hydrogen having 2 hydrogen living next door. What about this one? This one?
3. So actually, it's like 6.
There are 6. Very good. There are 1, 2, 3, 4, 5, 6 living next door.
So two hydrogen environment.
There are 2 hydrogen environments. One is the hydrogen environment of having 2 hydrogen living next door. Another one is the hydrogen with the 6 hydrogen living next doors. Okay, so you can just think about the tenant like a houses or the like a units too. If, when you have like you see the next door, there are 2 people living in, and some your friend's door friend's house living 2 people living next door to. I would say they're the same environment.
So can you say H1 equals to H1 like bar, like
Bar.
2H, like
Yeah, that'll be 2.
2H.
There'll be 2 the hydrogen environment as well too.
Yeah. So the first one would be H1, then
Yeah.
dash 2H,
Hmm.
and then the second would be
Good. Now,
6H.
what about this one? We have that in your example. Yeah, keton. This is known as a butanol. Okay, let's count the carbon environment first of all. I gotta count blue, red, purple, and then green. I have a green. Okay. Ian, can you describe the blue carbon here, the blue carbon's environment? Environment.
So 3 hydrogen attached.
There are 3 hydrogens, okay? There are 3 hydrogens attached, and
1 carbonyl.
there's 1 carbonyl living next door. Good. What about red carbon's environment?
It has double bond.
It has attached to the double bond oxygen and
Has one CH2.
we have a 1 CH3 and
1 CH2.
1 CH2 living next door. Good. What about purple?
It has 2 hydrogen attached.
It's a 2 hydrogens attached with
1 carbonyl.
1 carbonyl and
1 CH2.
1 CH3 living next door. Good. Last one, green.
Has 3.
3 hydrogen living inside and
Yeah, and 1 CH2 attached.
1 CH2 is attached. Now, so comparing the carbon environments we have for each of the colors here, is any of those are the same carbon, having the same carbon environment, same environment in here? All of them having different environments. So there would be what? There are 4 carbon environments. Does it make sense here? Okay, let's move on to the hydrogen. Use the same color up here. Donghyul, tell me about this hydrogen environment.
You have to go through all of them.
I mean, I'm just giving you the orders to here because we're gonna practice that. I know there are 3 straight away, but you gotta determine that because you get something a little complicated later on. Donghyul, tell me about this hydrogen's environment or hydrogen's neighborhood.
So in the neighborhood, there's only like oxygen.
So is there any hydrogen living next door?
No.
There's 0 hydrogen living next door. Okay, with these having all of those 3 hydrogen here. Okay, what about this one, the purple?
They'll have 3 hydrogen next door.
Okay, there are
Oxygen.
Wait, I don't care about oxygen.
0 hydrogen.
Yeah, there are 3 hydrogen living next door. Yep. Okay. Jung, you alright, Jonghyul? Okay, Jongmin, yeah.
So I should think of carbon as like a house. So for this one,
Yes.
for the COO, it has 5 hydrogens living next door.
But it doesn't have a hydrogen in it. When we count it with the hydrogen environments,
Other children.
yeah, we just look at the hydrogens. Yeah, we can think about hydrogen as a children too. We just count it, hey, how many children, how many like hydrogen living next door?
So see
For the hydrogen perspective, so you can match. So this hydrogen, I just count for these hydrogens,
that's 0 hydrogen.
0 hydrogen living next door.
And then that one, CH2, has 3 hydrogen living next door.
Yes, very good, because they're on the next door here. The green hydrogens are living next door.
So there's 3 hydrogen environment.
In total, it's because like here, the green hydrogen only have 2 hydrogens living next door. Okay, so in total we have a very different hydrogen environment here again. Yeah, which makes that there are 3 hydrogen environment in total.
Sorry, for the hydrogen, right?
Yeah.
Do you count oxygen?
No, we only count for the hydrogen to hydrogen, carbon to the carbon, because oxygen would be something like out of nowhere. It's like basically not counted.
It's the parent.
Or like grandparents, oxygen.
Give us a little bit of time to complete that.
Don't worry, I give you the exercise today. Could you pass that? Now, from that the exercise sheet, could you determine the number of the hydrogen and carbon environments for all that?
All of it?
All of it. So, number 1, we have ethanol. So, just have a think of like, look at the 1 carbon's perspective, see what's living with, and see the neighborhood. So, this carbon here, this carbon 1 over here, is living with 3 hydrogens, and then next door there are CH2. Okay, so and this carbon 2 is living with 2 hydrogens and different neighborhood compared to the carbon 1. So I would definitely say there are 2 carbon environments. Okay, for the hydrogen environment then, have a think about these 3 hydrogens living in the first carbon. These 3 hydrogens living with, they have a neighborhood like a 2 hydrogen living next door. For this one here, this is interesting, this is one thing you need to know. For this hydrogen, we don't count the oxygen, guys. We only see the carbon next door. So they'll be having 3 hydrogen living next door. Because oxygen will be like a departing, making them more separated here. We don't really count. Will be something on the street. You can imagine that. And this hydrogen here is definitely, it doesn't have any hydrogen living next door. We don't really count that oxygen. Oxygen will be like separating everything. So there'll be 1, 2, 3. There are 3 hydrogen environment in that reason. Let's do the second one, the butanol here too. Carbon 1, 2, 3, and 4. Can you see like carbon 1 living in 3 hydrogens? Okay, having 1 CH2 living next door. Carbon 2 living with 2 hydrogens with 3 CH3 and CH2 next door. Carbon 3 has 2 hydrogens. And this time, it seems like, hey, isn't carbon 2 and carbon 3 having the same number of hydrogen living in? Yes, but you have 2. Carbon 3 and CH2 living next door. Carbon 3, however, living CH2 with COOH. That's definitely a different neighbor. Means that there are, and obviously this is a different carbon environment as we can see. So there will be 4 carbon environments in this case here. Yeah.
For the fourth one, wouldn't it have the same neighbor as the first one?
Is it? But it's living with the oxygen. With the 1 hydrogen.
So we're not actually looking at the neighbor, we're just looking at the...
No, we're looking at both. Good, thinking about the environment, your environment. Okay, when I ask you, hey, tell me about your environment means I'm asking your living environment, like living environment as in like how many family members you have in the house and what would be the neighborhood as well too. That's how we can describe the environments in here. Okay, look at the hydrogens. Hydrogens, we have 3 hydrogens that's having 2 hydrogen living next door. There are 2 hydrogens from carbon 2 have 1, 2, 3, 4, 5 living next door. Okay, for these 2 in the carbon 3 have 2 hydrogen living next door and 1. There are 3 hydrogen living next door. For this one, it has 2 hydrogen living next door only. So it seems as, hey, but isn't that hydrogen and these hydrogen having same environment? But there's an oxygen. And that makes a difference in here. Again, the hydrogen would be like a different environment. Because we have to count, if we have a same environment, means that they would be symmetrical. If we had the shape of this, butane, for example, in here, okay, I would say, hey, these hydrogens and these hydrogen have the same environment because they're symmetrical. Okay, but as we can see, like this is not symmetrical. There's a 1, 2, 3, 4 hydrogen environment here as well too. Is it clear? Is it clear?
So you need to take into account the oxygen when you're doing hydrogen environment.
You do, because you have to think about
If
it.
there's the oxygen, it makes it totally
It's different environment. Yeah? What about this one? It's kind of easy. There's a 1 carbon environment, 1 and 1. So 1 hydrogen environment, 1 carbon environment because these are symmetrical, and 1 carbon environment as well too. Sorry, 1 hydrogen environment here. Propanol, how many? 3 and 3, correct. Ooh. So 3 carbon environment and 3 hydrogen environment. Next one. Can be. So in between here, it's hidden. There's a carbon. There's a carbon here. The joint line means there's a hidden carbon there, and it has one hydrogen hidden. There are two hydrogens hidden inside that too. Now count how many would be how many carbon environments we have. The three. We have one which is symmetrical. Okay, this is kind of definitely like a different carbon environment, and that too. So there are three carbon environments. Very good. Hydrogen environment then. There will be 1, 2, and 3 hydrogen environment. Next one. What about pent-2-ene? This is interesting.
Is it 3, 4?
3? Are you sure it's a 3?
I'll go 5 for it.
You had a 5. So carbon environment, it's a 5.
Yeah.
Each individual carbon have a different environment.
Can you just look at the symmetry?
You can look at the symmetry. You can look at the symmetry to find the same number of the carbon environment, but also looking at the individual carbons too.
How is it 5?
Why is it 5, Dongyu? Jongmin.
Because, how do I explain? They all have different environments.
Yeah.
Like CH3 at the... Are you confused by the double bond?
Yeah. Doesn't like the third one and the fourth
I-
one have the same?
Can you ignore the double bond?
You do not. You do not.
Yeah, so
Okay. Look at these carbons. Okay, if that confuses you, 1, 2, 3, 4, and 5. Dongyu. Carbon 1 living with 3 hydrogen next door to CH2. Clear? Carbon 2 living with 2 hydrogens, now having CH3 next door on the left hand side and CH in the right hand side. Carbon 3 having 1 hydrogen only, having CH and CH2 living next door.
oh, doesn't the fourth one have the same as?
Both one? No. Both one have CH3 next door with the 1 hydrogen living inside.
Oh, so do you,
This one has 1 hydrogen living and CH2. They are different. So it's a distinctable carbon environment.
Wait, so... What about the double bond?
Yeah, but double bonds giving that a different number of the hydrogens anyways. What about the hydrogen environment? There will be, this is definitely, there are 2 hydrogen living next door. So for this, there are 2 hydrogen living next door. For this one, there are 4 living next door. For this one, there are 3 hydrogen living next door. It seems like I have a 4 hydrogen living next door, and this one has 1 hydrogen living next door. So that'll be all separated hydrogen environment, which is 1, 2, 3, 4, 5 in total.
Which one? Oh, yeah.
But doesn't carbon 2 and 4 have the same amount of hydrogen living next door?
Carbon 2 and 4, but they one is attached to the here, the living like
Oh.
yeah. You have to look outside as well as inside. We only say like they are having the same environment when they're identical.
So it's benzene, just 1,
Benzene. Oh, how many carbon environment?
1,
1
1.
and 1. Good. Because benzene means we have a carbons, okay, with the 1 hydrogens each. And they are, or just think about symmetry here. They're all symmetrical.
but don't they have like double bond and a single bond?
Well, still be the same.
Or for the carbon, the number of bonds doesn't matter.
For this one, benzene,
Yeah.
all that carbons in the benzene will have the double bonds
So,
with the 1 single bond.
yeah, like one single, one double, one single, one double.
Everything.
One single, one double.
Yeah, everything.
That's
6 carbons with 1 single, 1 double bond, 1 hydrogen. Same environment. And all the hydrogen would have 2 hydrogen living next door.
the helium,
All that.
You have like
Hmm?
18 bonds.
Hmm?
Benzene.
18, what? Sorry?
So you said like there's 1 single and 1 double in each.
For each of
carbon.
carbons, yeah.
You mean like the
No, I'm just talking in terms of the carbon's perspective.
all the
Yeah?
things.
I didn't count them. What about this one?
It's 2C.
Oh, hydrogen environment, there are 2 carbon environments. Good.
And 1 hydrogen.
Yeah, 1 hydrogen environment. Very good. You're getting there. Now, challenge the aspirin and paracetamol. I show you the hidden carbons and hydrogens. So this is the hidden carbons,
Then 5C.
and that shows the hydrogen here. With the one, there's no
Which one is
bonds
Oh,
here.
how am I supposed to do this?
Okay, and paracetamol have hidden carbons. Look up here. There is the hydrogen, 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 and hydrogen, and CH3 there.
Are there 6?
For what? As
Environment.
aspirin or the paracetamol?
Oh, the aspirin.
No,
7,
no,
Oh,
5,
no.
8.
5. It's not 6?
No. It's not 6. It can't be 6. Guys, write it down. Like, if you're not too sure, write it down. Like, think about what's living with, what has a neighborhood next door, and compare them. 9. Correct answer. Write it down. Like, if you don't have any idea,
Oh,
write it
the bottom
down.
very end.
Yes.
Oh, shit.
Yes.
What do you mean write it down?
Like, write it down as like this carbon has 3 hydrogen living with, and there has a CO. If you don't, if you're not too sure, write it down as He. You can compare them.
In the benzene, then you have like 4 same bonding.
Really? Are they the same?
They're all not very similar.
How?
You mean these two? Are they the same?
Not those two right now.
They're all different in this benzene.
Very-
They're all
very
distinctible.
important, right?
Yeah. 3 bonding.
This one too,
Yeah, those two. They should have the same thing.
because they are okay. Look at this. Are they symmetrical?
Do you have to like look at it in terms of like
What kinds of like environment terms? Yeah, we do. So there are 9 carbon environments.
Okay.
Hydrogen environment. We have 1 separated hydrogen. We have a 2 separated hydrogen. Okay, and there'll be 1, 2. So these. Let's have a look at these here. This hydrogen had 2 hydrogen living next door. This has 2 living next door. So the same environment. Okay, there'll be 1, 2, 3, 4. What about these 2, John? Are they the same?
No, they don't know.
Are they the same or different?
They'll be different.
Why?
Would they be the same?
They are actually the same hydrogen environment, I would consider. So there'll be 4 hydrogen environments.
Oh, I said 4.
1, 2, 3, 4.
And for the carbon environment, you have to look at the whole structure. The hydrogen, you just have to
Look at the, like what you're living with, and look at the
You just have to look at the carbon, hydrogen, right? The hydrogen.
next door.
next door.
With carbon, you have to like look at the whole structure.
Whole kind of house structures, yeah. Or you have to look for like a symmetrical or asymmetrical shape. Paracetamol.
Can you give us some time?
I'll give you 2 minutes.
Is it 5C?
No.
Six.
There'll be 6.
I forgot the C.
The last one, yeah? Yeah. Did you find the symmetry?
Is there a symmetry?
Yeah.
And 5H.
These 2 are symmetrical. These 2 are symmetrical too.
Yeah, but if you look at the other way, like the structure is different.
What other way?
You cross the line in the opposite direction, like perpendicular.
This?
Like that.
Why would you do that for? Okay, I'm looking for one symmetry here. Okay. Looking at this symmetry here,
This kind of shape.
it's a shape.
There's a
You can
symmetry.
symmetry is like you can fold them and make in the mirror kind of mirror image.
That you're gonna cut it down.
Mm.
So the symmetry is going like this. It's not like a square.
We're not looking for the perfect symmetry of the every single side. As long as one side of the symmetry. So like for this one here beforehand, there's symmetry because we have access of this. Wasn't it?
So 5 hydrogen.
So 6 carbon environment and 5 hydrogens, you reckon? So these two will have the same hydrogen environment as well too. And same for this one here. So the 1, 2, then we have a 3 on this side here. It doesn't have a hydrogen, so we have
Carbon in the very middle, like
here,
the
here.
yeah.
That has no hydrogen.
No, actually.
Thank you.
Okay.
Oh, that was nasty. That was so nasty. Okay. Oh, okay. So we don't. This has a full bond, so we don't count this. So we have 1, 2, 1, 2, 3, 4, and 5. There's a 5 hydrogen environments in totals.
I went to the toilet, please.
Yeah, we're gonna have some break.
Carbon. Why isn't there carbon in the middle?
Let's move back. Let's make chemical like those environments. Let's move back to some of the this molecules here again too. So as I explained about NMR basically like think about spinning of here. So you can assume that if we have something really electronegative attached on the carbons, it affects the whole spinning process of the carbon and the hydrogens. Now that is actually be described that as chemical shift. So the more electronegative the neighboring atoms are, so for example, when we have oxygen, chlorine, and fluorine, the less energy required to flip the hydrogen nuclei. So which means this is because the electronegative atom will cause the electrons orbiting the hydrogen nuclei to spend less time with the hydrogen and more time with them. This is the hydrogen nucleus is less shielded and more susceptible to radio wave interference. Highlight this point in here. Just in the last day of the preparing your trials, I would like you to memorize it. Just one sentence.
Last day.
This is just the last day. So this is explaining you how does chemical shift work, or like explain chemical shift work in the NMR. It simply means more electronegative atoms will kind of make a shield, like less shielded. So shielded as in like there's some radiative, make them to be less rotated. So what we expect is when we're having something electronegative attached, so shown in the next page, page 162. Okay, let's determine some number of the carbon environment first of all, and then see what we have. What we have in here. We have a carbon that is blue and purple. We have a carbon that is blue on this side here. This carbon in blue is attached to the chlorine or chloride, which is very electronegative. Now, as we discussed that before, the chloride is making that less shielded. Less shielded as in like it making to be more shifted to the left-hand side. So you would actually see that the chemical shift of the carbon with the chloride will more onto the left-hand side. So this is the rule that you can find from those carbon NMR. So rule number one, the more electronegative attached to carbon will be more shifted to the left. Okay, so the blue peak is showing that the carbon with the chloride, because again, chloride, which is electronegative, is making more de-shielding effect. Make them to have more shifted.
It's also left.
To the left, as in terms, because we started from 0. Now, TMS stays for the just the standard line, like a controlled. Okay, so TMS is always started from 0. So don't worry about the TMS. It's just starting like you can think that as some sort of the axis, like, or the standard line in here. What we have to concern is first chemical shift of the carbon. 2, the number of the peaks. The number of the peaks. Now, for this chloroethane here, there are 2 carbon environments. One carbon in the purple has living with 3 hydrogens, and next door there's carbon with the chlorine next door. This carbon blue has living with the chlorine and CH3 next door here. Definitely different carbon environment we can see. Yep. Then the number of the carbon environment is something that you can remember too. For the CNMR, carbon 13 NMR, the number of the carbon environments is actually same as the number of the peaks on the NMR. For example, from the example of the paracetamol, we had a seven carbon environments. Means we would expect to have 7 different peaks in the carbon NMR in here. Yes, Ian? Did you have any questions?
So that, you know how the electronegativity,
Huh?
how does that affect the spinning?
You can think that as when something is attached really strong, is you're holding your neck.
So it's hard to spin.
It's hard to spin. It's more to be like de-shielded.
But why is that shift to the left then?
Because shifting means like if they're perfectly shielded, shielding as like they're shielding their radio wave, okay, means that because of the shielding effect, they got kind of shielding perfectly. There will less movement, because they can shield.
Well, so it's like the more left it is the how much better.
How much better like it can all kind of there. Or you can just remember that as because it's kind of really complicated. I need to use some physics terms or Bohr's model to explain that. Let's not go there. Okay, it just simply just make it really simple, just like IR. More to the left. It's attached to the more electronegative element. That's it.
Yeah.
Yes.
So if the breaking bonds, would CL break first?
What do you mean breaking bond? I didn't say anything about bonding breaking.
Is it different?
Yeah.
Like when electrons are...
No. Don't mix use that. Don't mix use with the mass spectrometry and NMR. NMR spinning of the elements or spinning of the electrons. Mass spectrometry we're cutting. We are like fragmentizing. We're not fragmentizing this one.
Greater electronegativity will be shifted towards the left.
Carbon with attached to greater electronegative elements shift to the left. More shift to the left.
So the more to the left, the more to the stronger electronegative element.
Yeah. So page 164 shows explains you no guys, just look at this. Have a look at this. This is what I mean. Like when the carbons attached to these over here, you just see it depends on what the carbon's attached with. When the carbon is just with the carbon, it will have a shift of the range of 5 to 40 ppm. Okay. Now, when the attached to the chlorine or bromide, it's more further to be shifted to the left, which is to the left-hand side. Okay, we start from 0 to on this side here. Can you see the carbonyl, which is also be what like an electronegative or oxygen? It has a shift of 20 to 50. All right, and then we have carbon to nitrogen, and that's 25 to 60. Alcohol, ether, and that. All right, you will be given this in your data sheets. You will be given. You don't have to memorize. I don't really recommend you to memorize any of these numbers. Okay, so this is why. Okay, I'll give you that actually. I'm gonna use this today.
For the second one, the third one, what can you say is more like electronegative?
Don't. Unless you want to study that in the university. Okay. I just give you a shortcut. Don't take the long way back. Okay, you won't get a question like why is that? No, you won't get the question. Let's go straight forward to you gotta learn how to solve the question. You alright, Joe?
Oh, so that's...
You okay?
Yeah.
You okay? Oh, Zhongmin, stressed. Okay, so as we can see, when we have this is not actually known as benzene ring. So when the benzene rings attached, it will be more shifted to the left because it have a more shielding effect in that case. All right, shielding effect. So it's given over here.
Benzene very electronegative. But what's benzene made of?
Benzene is kind of absorbing. So page 161 explain here. The more polar group, the less shielded. More polar groups, less shielded. Hydronuclide is by own electrons, therefore more effective they are by radio waves, correct wavelengths. So the more electronegative neighboring atom is that, the further this peak will be downfield or the shift to the left. Okay, simply when you attach to something really electronegative, less shielding effect, therefore more shifted to the right. Just memorize it. Don't understand it. Do not have to. Just memorize it as more electronegative attached, less shielded, more shift to the right, more shifted.
And why is chlorine like shifted to the left? Because it's electronegative, isn't it? Didn't you say if it's the more polar, right?
More polar, more electronegative, more electronegative, more electronegative carbon attached to shift to the left.
More
What about this one?
electronegative.
What about what that one?
So why does it? What do you mean less shielded?
Okay, Ian, this is what I'm saying. Don't try to understand here.
Yeah.
Shielded as in like you have to think about like in the radio wave, how to protect the radio wave in the factors too. Just accept it as more electronegative elements attached.
It is what it is.
It is what it is. Less shielded, therefore showing on the left hand side. Is it clear?
Did you say the more shielded you are, the more shielded?
More electron. Write it down somewhere. Come on. More electronegative elements, less shielded, more shifted.
Isn't that just the third dot point?
Yes. I've been reusing that for like 10 times now.
Do we have to know about the bondings between C and CO? It doesn't matter.
Of course, you know what the bonding is, but you don't have to.
You don't have to. It's
Okay,
not related,
don't you tell me. What do you need to know for this NMR then?
Just like the electronegative.
Do you really need to know about electronegativity? What did I say? What did I?
More electronegative.
Is
To this carbon.
yeah.
It will be more shifted to the left from the zero TMS, and it will be less shielded.
Good. That's all you need to know.
That's all.
All you done. Full stop. Don't cross the line. That's the boundary. Don't cross the line. If you go across the line from here, you're making your life misery. Like really. Don't.
When you're talking about electronegativity,
Yeah.
that it's the strength of someone holding like a neck.
Some sort of that. It's kind of so less shielded means like a less protection. Yeah. Shield.
When someone's holding a neck,
They can't spin.
oh, so that's what you mean by
Yeah.
less shield.
Less shielded. What makes this okay? What makes it spinning is a radio wave to kind of hitting that carbon and the electrons to make a shield, make it to be rotated.
Yeah.
As you're like hitting that something to rotate. Okay, so if that's surrounded by hydrogen giving some good shield or the protection, so there will be less movement in there. But when it's hold by something more electronegative, this is why. Don't freaking cross the line. Don't make me explain this again. I'll be really angry with it because we don't have a time for this. Okay, means that simply they have more holding that, giving the less protection, so that there will less spinning process, more shifted to the left again. Easy.
Can you explain that? No, I'm kidding. I'm kidding.
I think it's just the word shield is a bit like.
Yeah, but that's like how we describe the process here. Like shield as in like a protective, like a shielding effect.
Give us an explanation question. Can you say shield?
You can say like more shield. Yeah, it's appropriate to use a shield. The less shield, that's all less shielding effect, less protection. All right. So this is what we can see for the ethanol, guys. We have an ethanol, which okay. No, don't not now. Don't now. Give me 10 more minutes. You're not allowed to ask me any question for 15 minutes now, because I need to go through this first. There's an ethanol here. Okay, ethanol has, as we can see, as we learned the carbon environment, it has a 2 carbon environments. Can you say that? 2 carbon environments, different carbon environments. So the number of the peaks must be, there are 2 peaks here. Now, the carbon in the pink or the red is attached to the oxygen. As we discussed that, carbon elements have a less shielding effect, therefore more shifted to the left. Just memorize as a phrase. Carbon with the more electronegative element, less shielding effect, shift more to the left, as we can see in here. All right? So by looking at that, without looking at this over here, by looking at the peaks, then what you need to think is, oh, there are 2 carbon environments. Okay, past means that having 2 carbon environment means the minimum number of carbon must be 2. The minimum is 2. I wouldn't say 2 exact yet. Same in here. The ethane has one carbon environment. Can you see that like shift is not that much significant? It's only be on here because it has only the carbon with the hydrogen. Follows the range what we have in the data sheets as well too. All right, so number of the carbon environment is the first information. Number of the carbon environment, the CNMR can be shown by the number of the peaks in the NMRs, CNMR. 2, the shift of the peak is indicating that the presence of the electronegative element.
Can I ask you one thing?
It better be a good question.
Because they write 13 in front of C. Like,
Huh?
13C, right?
What?
In the textbook it says
What? Which one? Sorry. Okay. Which one? This one?
C13.
C13, yes. Carbon 13.
It's isotope.
It's isotope.
Like the never mind.
Is that what you're asking? Okay, the reason why we use carbon 13, specifically carbon 13, we must say the carbon 13, not the CNMR. Carbon 13 is it's more have an extra electron means that they can have more spinning effect. So we count for the carbon 13 for the NMR, but for the hydrogen, so it's not the hydrogen 2, it's just hydrogen 1. Okay. All right, 4.1. Next page. Determine the structure of the and identified of the alcohol. This is the kind of questions you can get. You know the functional group from the IR or from the chemical test. Now you're given CNMR, look like this. Okay, by looking at CNMR, information 1, as we have a 2 peaks, it must be the 2 carbon environments.
Ethanol.
It'll be most likely the ethanol because having a 2 carbon environments and having 1 is attached to the further shifted, that must be this is representing carbon with the OH is attached. This must be carbon to the carbons attached. This is the information that we can use. This is all you need to do.
If I ask you why, do I get
Why for what?
C or H?
Bro, be careful, man. Get the couple one, get the couple one.
No, I mean like.
This is what.
Okay, ask away.
It better be a good question. You better.
Right, the COH.
Yeah.
CC, how do you know?
Yeah. All right. Question 2. The CNMR for the isomer C3H6O is shown below. We have 2 isomer from 1 molecular formula here, 2 over here. Now, identify each isomer and justify your answer. This is what the information you can get. You can get some molecular formula. Huh?
First one's propanol.
How do you know it's a propanol?
There's 3 lines.
Oh, okay. Let's go over here. We have isomer A, first of all here. Describe the information we can get from this graph.
The very far one. The very far one is probably
Carbon environment.
Okay, so let's start from the 3 carbon environment. And
Is it propanol?
okay, and then we have the carbon that must be attached to really highly electronegative. Okay, now time to use your data sheet. It's giving you the range of something, the peak here. We have a range that's about like a 210.
It's aldehyde or ketone.
It's aldehyde ketone. It tells you, this is how you use it.
So do you look at your furthest one?
Well, I can use they can use the peaks over here. It tells you the range of that.
Or just use
Use them all. So we have a peak at the further the peak, 210 ppm. According to the data sheet, it's giving you it's out to be what? Ketone or aldehyde. So it's out to be something, the ketone aldehyde with the 3 carbon environment, and the molecular formula is C3H6O. Guys, think about it here. This is why you need to use your brain. Think about like what? We have 1 oxygen. From all the functional group you learned, you only know 1 or 2 having 1 oxygen, except the alcohol. This is not an alcohol. Maybe alcohol, maybe. Could be an alcohol. But it's gotta be a ketone or aldehyde with the 3 carbon environment. Means, draw 1. This is a hydrogen, CH2, CH3. This is what? Propanol. This is aldehyde. Now, the reason why this cannot be the alcohol is because of the molecular formula too. To get the molecular formula of the alcohol, we must have a C3H7.
2n plus 1.
Because we need to have extra hydrogen for the OH.
Would it be H8?
H8? Yeah, could be possibly H8. Or C3H7OH. Some form of that too. So this is why we need to think about like this. Because the HCC question will be exactly forms of those. They make you to think. Alright, so let's check here. Isomer A possibly be the propanol, as it has a 3 peaks from the 3 carbon environment. Can you say 3 different carbon environment here? Yep, and it also has the peak at 210, which is talking about this peak. This must be the peak of 210 ppm.
So it's propanol.
Yeah, it's a propanol.
So that's
This
3
peak
peaks.
is represented by the 39 over here. This peak CH3, most the less shifted must be the CH3.
Oh, so isomer B has to be ketone.
It's got to be ketone. It could be the ketone. Why? Why is that? Why is it has to be ketone?
2 carbon environment. So
We have a 2 carbon environments. Very good. And
It has the peak.
it has a peak. Yes, it's shifted at 210 here again too. The shift at peak at 210 ppm represent what again? It's either be ketone or the aldehyde.
4.1.
But as we have the ketone, as we have the aldehyde from here, it'll be the ketone shape. Does it have the C3H6O? Yes. Does it have 2 carbon environments? Yes. This 2 having the same symmetrical, same carbon environment, having 2 carbon environment here. Does it have the functional group of the ketone? Yes. So this must be isomer B. What are those isomers? What type of the isomers are they?
Functional.
They are functional group
Functional,
isomers.
functional.
Functional group isomers. Prepare that for the next week. Next one. A primary alcohol has a molecular formula C5H12 and O, and it's C3. Okay, I want you to give it a go for this one here.
But the values like overlap.
What values? Yeah, there are the ranges are overlapped,
Yeah. Which one would you pick?
but it's given that the functional group is the primary alcohol.
No.
It's given. Do you guys get it? Oh, this is why you need to think first. How many peaks do we have? So there'll be for possibly 4 carbon environments, aren't they?
One has CO.
Okay, now have a thinking here. If you're given the C5H12O, that's a molecular formula, but we only have, from 5 carbons we only have 4 carbon environments. means if you throw coming from the other end, that means that there must be two carbons having a same carbon environment. Okay? So to make that possible, because we have 4 carbon environment with the 5, they're possibly having a methyl.
Is it diamond? Oh, it's just
Methyl attached. Having a methyl means that yes, there's a possibility having the same. Methyl must be attached at the end. This is why you need to think about it in here. So can you think about here? So you can think about carbons, 4 carbons with primary. It's given the primary. The OH is attached in here with the hydrogens, the primary, and then at the 3rd carbon we have a methyl. How about this? How about this? Can we tell, oh, this one has 5 carbons, but as I can see, these 2 have the same carbon environment. They're symmetrical, aren't they? They're having same carbon environments, so that we can now have 4 peaks over here. Is it clear? Okay. So OH must be the something carbon with the OH attached. Okay. I would say that as it's a stronger signal, this is probably the CH3 attached at the end. We don't know. You don't have to identify which is which for this. It's not the point. As long as we get the correct structure of this, the alcohol. So name would be the 3-methyl 1, 2, 3, 4. The butane 1-ol. That's the name of this. Okay, so guys, when you have the many number of carbon but less number of the carbon environments, have a think about it. You have to question about, oh, there must be some carbons have the same environment, possibly have the methyl attached. Yeah?
for that question. If you just look at the formula sheet,
Yeah.
you can see it's alcohol, ester, or ethane.
Do we need it?
Like, can we just
I mean,
say
do we need to use that today?
it's given?
It's given.
Yeah, because we know that. Can't you just rearrange the equation to get just alcohol? Other than
What are you on about?
it's given now.
It's given. I've been saying it's given. It's given. It's given. Okay. That's right. But you can confirm the person's alcohol using data sheet. I can take that. You can see like alcohols over here, this peak over here, which is shift of this 70 or something. You can use that to confirm that this is alcohol functional group. Confirm. Confirm is important because you can find the functional group from where? From?
The ion.
From IR. You get to confirm the from IR, or you can even use. Do you remember the chemical test we did? Chemical test of the alcohol, sodium metal test. That's what too. You will get various data, various result of that, and you need to identify what the compound. This is the task of the 2 chapters.
So what happened to the TMZ?
Oh,
Is it just the first one?
It's just the first one. I don't know. It's just it should be here.
Yeah.
It's not really
It doesn't matter.
TMS. It doesn't. It doesn't matter. It
Did
does.
they ever give you a question on the TM then?
There's once.
In the HSC?
No trial.
HSC trial.
What's the team?
TMS is like a standard line to make the comparison to the other pictures. So
The DMZ.
yeah, more TMC. Yeah. What's the TMC? TMS stands for like a standard line, it's a starting point. There's 0. Okay, so we can compare them. Any questions about carbon NMR, CNMR?
Oh, there's another.
There's a H.
Of course. I told you we're gonna finish it late today.
Yes! Yes!
We might finish at 8.
Worked on NMR. Oh my gosh.
Yeah.
It's just what I want to see on a Friday afternoon.
Oh, I mean it, guys. We're gonna finish at 8. So prepare yourself.
Oh my gosh. Okay.
Let's talk about the H and MR now. Just like this carbon and MR, H and MR share the same feature. So same featuring as it will have first the number of the peaks in peaks on the H and MR tells you that the number of the hydrogen environment. And this is kind of tricky because you have to now think about, you need to think about the number of the hydrogen environment. It's more complicated. 2, chemical shift. Yes, just like a chemical shift, more chance, greater. the hydrogen near at the more electronegative elements more likely to be shifted, but it would be varies given over here. Now for the HNMR, this is the only data is not given on your formula sheet. So you don't have that. You don't have that CNMR over here, the HNMR given over here. But you don't need to memorize any of these data here. If you're given a data sheet like this here, this actually happened in 2020 HSC. If you're given a data, so right here, if you are, if data is given, the table is given, you can use to identify or to confirm the functional group. Only if you're given a data sheet. So for example, if you're given this kind of data sheet over here, you can use to determine like its functional group using the chemical shift. Okay, only if. There are some occasions you're given this, you're not, and they never ask you to memorize the data from here. They will never ever. This is not really part of the syllabus. Okay. So if we can use that, you are able to identify here. Now third, unlike the CNMR, there are some special features of the HNMR. One is we have to look at something known as chemical shift, and that we have to know something known as splitting of the peaks. This is also known as N+1 rule. I'll show you that what it means on the page over here. Look at the example of the page 172. Okay, we now have the CH3 and CCl, so chloroethane given over here. So carbon environment, there are two carbon environments. For the hydrogen environment, guys, you have the hydrogen environment, there are two hydrogen environments. So it's matching that, we have a two. We have a two peaks, two regions of peaks. Now also, the red hydrogens are more shifted to the left because it's near at the chlorine. Less shielded, therefore more shifted. Everyone agree with that? Clear? Up to here. Just like a carbon NMR. Okay? Guys, I'm doing with hydrogen. Do you have to separate the carbon NMR and hydrogen NMR separate here? Now, what you can see there is, you just see that this red hydrogen has four splitting. We call it quartet. The quartet signals here. This blue signal has triplet. So we can also have some doublet or pentlet, sexlet, and septlet, nontelet, so some split. Now, what does it quartet? The four signals given here is the signals, split signals tell you that the number of the, remember this, the neighboring, yes, neighboring hydrogen, not the hydrogen living in the house. It's telling you the number of the neighborhood hydrogens.
You're saying that it's 4.
So in here, quartet, so using the N+1, if we have the 3 hydrogens living or located living next door, there will be a 3 + 1 making the 4 split will be shown. This is known as N+1 rule. So there we get the quartet. For example, don't just give me a sec. These two hydrogen here, red hydrogen, has 3 hydrogen living next door. Okay? Can you say like just you look at the hydrogen living next door. These two have 3 blue hydrogen living next door. So showing that you must have the 4 peaks, 4 splits of that in here. Can you see that? Okay. Now for this red hydrogen, for this blue hydrogens, it has 2 hydrogen living next door. So for this own signals, it shows that there are 2 hydrogen living next door by showing the triplet given over here. Does it make sense? So it only reflects how many neighborhood, how many hydrogen living next door. So let's have one example using this. I show you the structure of the one carboxylic acid structure here. So we have carbonyl OH, CH, and CH, and CH3. So 1, 2, 3, 4. Butanoic acid here. Jongmin, how many hydrogen environment can we find from here? How many hydrogen environment can we find? There are 4. 1, 2, 3, 4. So 4 hydrogen environment. So how many peaks?
5. 4, 4, 4. Oh, 4. My bad.
Yeah, it's your bad. Okay, there are 4 peaks.
You're so
No, I thought you meant by split.
Huh?
My bad.
Okay. Jeremy, like we have a 4 hydrogen environments. For these peaks here, do you expect that some shift?
Yeah.
Which of the hydrogen will be most shifted?
With the O.
With the O. This is probably the most shifted peak. We would expect somewhere in here, on that left hand side.
What about the double bond?
Yeah? What are you on about?
What about the double bond?
Why are you talking about oxygen here? I'm talking about hydrogen. Ian, wake up! I'm only dealing with the hydrogen. I'm talking about hydrogen only. Don't give it the oxygen here yet. Okay? Alright. Let's count the number of the neighborhoods then here. For this hydrogen, Ian, how many hydrogen living next door? For this hydrogen? 0 hydrogen living next door. Okay? For these hydrogen, same here. So these 2 hydrogen, they are identical. So Dongyo, how many hydrogen living next door?
2.
There are 2 hydrogen from this door here.
Oh, are they similar?
These 2 are exactly the same.
Can you
Compared to the other
Okay?
can you put a dash on the O and H so I can confuse? O and H.
O and H, do you want me to? Okay. Yeah. What about this one? How many hydrogen living next door?
5.
There are 5 hydrogen living next door. Okay, what about this one?
2.
There are 2. So it shows the patterns look like this. Even without looking that, I can tell that most shifted one will be located on the left hand side here. It will show the singlet, 1 peak here. It shows the singlet. Singlet means that it doesn't have a neighborhood. Now, for the 2H, for these hydrogens, what do you expect for the peaks?
The 2.
Yeah.
1, 2, 2.
So there will be, as we have a 2 neighborhood hydrogen living, there will be a triplet. So it's this hydrogen are also close to the O here, so it's more shifted. So it will show a triplet given over here like this. That's showing a CH2. That's showing the OH. Okay, Jongmin. What about this one?
6.
6. So it'll be have a 6. 1, 2, like this. 1, 2, 3, 4. 1, 2, 3,
How do
4,
you know where
5,
they're
6.
located? I mean, like OH, I know where that's located, but like the other C.
Closer to the.
We're close to. Or you can use
Oh,
the,
closer to.
or you can use data sheets provided here. Because for this chemical shift, it could be varied by what you are attached to. It's quite different to the chemical carbon. It's sometimes unpredictable, but I'm just giving you kind of estimate the location over here. But important thing is you only have a 6, so that from the CH2 again. Okay, the last one. What about this one? What about these hydrogens? They have a 2 hydrogen living next door, so it must show triplet. It will be triplet here like this. By looking at the splitting patterns, you are able to get how many hydrogen living next door, neighborhood. Alright, that's the third information we can get for the HNMR. Any questions?
Does the length matter?
Lengths? It will be more like showing the kind of structure like this here. So for example, next page, it shows the ethane structure here. So have a look at this. Ethane has 1 hydrogen here. How many hydrogen living next door?
3.
There are 3. So you would must have the quartet.
What is this N plus 1 or what?
The N means N stands for the number of the neighborhood hydrogens. Okay?
Did you
That,
learn that in uni? Why it's n plus 1?
you can learn that when you're studying the molecular science, molecular biology, or molecular chemistry, but not about the functioning of that too.
We don't learn why it's n plus 1.
Yeah, because you're not an engineer. That's a field engineering field.
Oh, like
Mm.
chemical engineering.
Yeah.
How much do you have to do to how do you get into chemical engineering?
You got a good ATAR.
Like how good of an ATAR do you
I don't know, 97 plus.
know? Really?
I guess so. All right, this is what? This is ethanol. This is what I mean. This sometimes the hydrogen attached to the oxygen will be less shifted than in here, because these hydrogen are really next to, rather than attached. It's more having a shielding effect. So this is something that you don't really need to memorize here, because it depends on the data sheet. If you're given data sheets, you can identify here. But what you have to see from the splitting pattern is these blue hydrogen has two neighborhood in hydrogen living next to, so that they must have the triplet, as we can see the triplet. Yep. Those red hydrogen, how many neighborhood hydrogen living next to? There are 3. We don't count the hydrogen and the oxygen. They are separated. So there'll be 3. So it shows the quartet here again. Lastly, OH will always be the singlet. So whenever you get the singlet, single peaks, you have to query, you have to questioning that, oh, it might be the OH. It might be the hydrogen attaching the hydroxyl.
Why?
Could be, like, you know,
There's a singlet line.
it's a singlet lines. Most likely about like 90%, but you gotta check it again with the other data we have.
What other occasion does it have?
It could have to carbon with just the hydrogen in some sense. Yeah, not the CH, having the CH next to, but even that will show the doublets. Okay, that's a third information we can get from the proton NMR. Everyone good? The last information we can get from the HNMR is something known as relative peak area. By the way, some schools not really teaching you this NMR or at all. They're giving you as a part of the depth study. So DIY. Yeah, that's tough luck.
Is that bad?
No, we got a depth study this term.
Yeah, that's really bad. Because they didn't learn how to do it in school. They just need to do it without learning it.
We got a depth study this term.
Is that area or oven?
Area.
That's oven.
Area. Just say. All right. Relative peak area means we are comparing. So by comparing the area of the peaks, okay, we can get the some relative values. There are relative ratio can be obtained, and that's relative ratio. That ratio gives us the number. This is important, guys. The number of the hydrogens in the environment. For example, giving you back in here, page 172, chloroethane, you have 2 to 3. Okay, don't worry about the peak area here. It will be given a peak area in the data too. So having a 2, peak area of 2 means that, simply means that there are 2 hydrogens. Okay? Having a 3 relative peak area means there are 3 hydrogens here. So, attached in that hydrogen environment. So, we have this peak here. This means there are 2 hydrogens next door with the 3 hydrogens attached. So itself means we have a CH3 that has 2 hydrogen living next door, which is this. Do you want me to interpret that again?
Yes.
Come here. 3, the relative peak area is given to 3. So only time we have a 3 is we only have 3 hydrogens attached to 1 carbon here, like CH3. Again, peak area tells you the number of the hydrogen in the same environment, which are these, CH3. This has a 3 triplet, means that neighborhood hydrogen must be 2. So only case we can get 2 hydrogen in the next door, we can have this. Does it make sense?
Because is it because it's 3 lines?
Yeah.
And so there's 3 hydrogen.
Yes.
So on the next one,
Next one, it has a 2 hydrogen living in the same environment,
why do you know it's because
and it has the it has a quartet, means that the 3 hydrogen living next door. Talking about this one.
Will they always give you peak area?
Not always. Not always. So if you're given a peak area, it's a really easy question because you know how many hydrogen living in there. Yeah.
What's the peak area?
It's the area of the peaks. So area is in like we count. The peak will be like something look like this. We actually count the area of those. This area of that too. Integration.
Integration.
But we don't do that in integration in here. This is why they give you a data that relative peak, the ratio area value
This is
here.
actually integration.
It's actually integration.
Can you do
Because you actually need to find the area. Guys, think about the area of this peak, here.
that integration it is?
Yeah, you gotta find like an area, but you won't do that. You will be given a data as a form of this 2 to 3, always, most likely. All right, or you gotta give a data forms like this. I show you the one HSC question in here. You will be given a data here. There's a proton NMR from the HSC questions. You say that there are 4 hydrogen, 6th hydrogen here. Okay, so without looking at any other data here, let's have a look at the data here. We have a triplet of the 4H, so which means that there are 4 hydrogens having the 3 hydrogen in the neighborhood. Sorry, 2 hydrogen neighborhood. 4 hydrogen with the quintet. Quint means 7. Okay, an overlay quintet over here as well too. Yes, this is what you will get in your HSC. 2020 HSC was questioned about. 2021 HSC was this.
Spectrum.
Yeah. So it was easy question because you just need to use those data to explain why the shape is look like this. Easy question.
I think I heard a complaint from like last year. My cousin and his friend were talking about how spectrum didn't really come out from the test. Right?
Was he blind?
Yeah, he was blind. Chang'e.
There was a you can check that in 2022 HSC. There was one 7-marker question.
Oh.
There's one 7-marker question. I don't get what I mean. Like we didn't get the spectrum. There was one.
Not many, but how many?
How many do you want then?
Did you do one in the HSC?
Yeah, Jaden.
Did you get band 6?
Oh, Jaden. He does chemistry.
Did you get band 6?
I don't know.
He's
Maybe-
smart.
I don't know.
Maybe not.
Tell Jaden.
It's ruthless.
He doesn't remember he had a spectroscopy. Guys, you only get one spectroscopy 7-marker question for per HSC, by the way, per trials.
Per HSC.
Are you sure?
Yeah.
That's just like a rule. That's just like what it is.
I can't give you two sets of the spectroscopy questions because there are other questions that I have to give you from module 5 to 8. No?
Is that the only thing we can get?
Possibly, yeah. I mean, this is the most likely question. So, multiple choice, some of these, yeah, a few, couple, maybe. But this is something that you will get. All right. Okay.
Let's go. 4.2.
Yeah, let's go. 4.2, page 174, please. Yeah, what the hell?
I'm going through something. I love it.
The proton NMR spectrum of the compound with the molecular formula, the C2H4Cl2, is shown below. Relative peak areas are shown on the spectrum. Identify this compound. Give it a go.
So the
Give it a
big
play.
numbers represent relative peak area.
What numbers?
The 1H, 3H.
Yes.
So that's a relative peak area.
Yes. And what does the relative peak area tells you about?
The number of high H plus in the environment.
Yeah, hydrogen in that environment. So how many hydrogen in that environment?
1,
That's 1 and
Oh,
3.
3. Good.
So it's 1 dichloro ethane.
which way do you go? Do you go to
Oh,
the
you
left or the right?
Too quick.
Hmm?
Do you go to the left or the right? So like you say, you put a C there.
But still, name would be the same.
Study.
Which one is
That's correct.
it's a one actual ethane.
Look at the formula and then.
Are you
That
sure?
one. That one. See that one on the very edge.
Yeah.
That means it's very close, right? That means there's 1 hydrogen in it. So it's ClClH. I see the 4 spikes. That indicates there's 3 in the. Okay, I might be wrong.
Is it?
Go, give it a go. Yeah,
It
keep going.
indicates there's 3 in the neighboring carbon.
Yeah. What about this one?
Ignore that one.
Hmm?
It's like 3 hydrogen.
There are 3 hydrogens with the double
Yes,
it.
so 3 hydrogen on the other one,
And yeah,
and
and
then 1 on the other one. So
yeah,
it makes
so
sense.
it makes sense.
It makes,
Is it-
makes sense.
Makes sense.
Is
Makes
it?
sense.
This is
Yeah.
1 dichloroethane.
Yeah,
Oh,
Is it correct?
yeah.
Yeah.
This is it.
Just 1 that. So I was right.
Yeah. There's a 1,1 dichloroethane. Why? Can you see that picture, Nick? Can you picture that now? This is the hydrogen shown on here. 1 hydrogen with the 4, with the the quartet means there are 3 hydrogens living next door. For these hydrogens, it's a 3 hydrogen for the relative peak area now having double it, which means there's only 1 hydrogen living next door.
but do you really need the area?
Can you do that without the area? It'll be harder.
Like,
It's easier.
It will be harder, but you can still do it.
Yeah, do it then.
Oh, not that much.
Do it. Question 2. It's not giving the area, John. As you wished.
I forgot to.
Is it called double it? Double it?
Double it.
Or double it?
Let. So singlet, doublet, triplet, quartet, pentat, sextet, pintat, heptat, well, some goes like that. Octet, yeah, goes in that order. What would be this one then, guys? It's a haloalkane with the 2 chlorines again.
Oh, so it's just.
Split-wise, there's a 1, 2, 3, 4, 5, 6. There's 6, so it's a sextet. And that's a doublet, just in case you guys missed it. And there'll also be doublet. And as you said, the relative peak area is not given.
So much confusing.
Is it 1 2 dichloro propane?
Anyone?
Well, you can. 1, 2, 3.
Jeremy, what'd you get?
I see.
No, you try it. I
got it.
promise you, I will give you these questions next week. I promised you.
Go.
You will get 7 marker question. I even can tell you the marks you get. It's gotta be 7 marker.
It's just.
Mine, like,
I don't know.
activist. What do you
Is it 1, 2 dichloropropane?
Yeah, that's what I got.
want?
Anyone else?
Is it 1, 2?
Hold up.
I forgot how to.
No.
Yep. Yeah, one. Okay, start from here. Jeremy, how many hydrogen environments can we find from here?
No, I'm right.
There are 3 hydrogen environments.
Wait a second. Wait, hold on.
Why is it not 1-1?
Okay. Wait, let's see. It must be the 3 hydrogen environments. Okay. And let's talk about the each over here. So start from doublet. Okay, guys. What does it mean by having a doublet?
That's one hydrogen around.
So as we think about what we have 1 hydrogen here, the next door, in the next door.
Wait, doesn't mean one hydrogen in the neighbor?
Yeah, it's a neighborhood. It must be the next door in the one neighborhood there. What about the doublet here? This means, for this one's perspective, there's one living next door too.
Oh.
Okay. But what about the 6th one?
6th one? How many hydrogens are living next door?
5.
There are 5. So how can we make the 5 neighbors? It'd either be one would be CH3, another would be CH2. That's the only time you can get the 5 neighbors if you have located it here. Can you see that? In this one's perspective, it has a 5 hydrogen.
Oh,
5. 5 is a very special number because we can have either be CH3 or CH2.
And then there's carbon connected.
And the rest would be just be chlorine. Does it make sense? Does it give you a clear picture there?
That's crazy.
Next
How
one.
did we think of this as humans? Like what? Imagine if no one discovered this. Imagine how good our life would be.
All right. I'll show you one question. Page 181. 2020 HSC question.
Is that an MI? No, that is not an MI.
2020 HSC questions here, guys.
Okay.
Page 181. 7 marker. 7 marker. 7's marker. How are you gonna do that? Okay, let's do. Give you about a few minutes to think about this question here.
Is it an aldehyde or a ketone?
I don't know.
It is.
You tell me.
It is.
Okay. You can discuss. Give you 7 marker or 7. Why you keep saying cat 7 marker question? Like in your HSC or trials, plan your work. Don't jump in and don't just write anything. Don't write anything before you plan anything. Plan here. Plan as in like think about what information you can get for individual of each of these graph here. So start from IR. Start from IR. What we get? I can see the very clear, strong, and narrow peak at 1680 to 1750, indicating that this telling me there's a carbonyl present here. Okay, there's a carbonyl. Now, what I can also see there is no signals of the OH, no signals of the OH at around 3000. Okay, there will only be a carbon with the hydrogen here. So based on here, we can just guess about the functional group because IR, remember that we use IR to determine the possible functional groups. The only functional group that we learned by having the carbonyl but doesn't have the hydroxide, doesn't have the hydroxyl, would be either be aldehyde, ketone, or the ester. So your functional group must be one of these. Okay, that's all we can get. We can't get anything out of it, the IR. So it's done. Now, next one. Let's go for the CNMR. CNMR here. Carbon 13 NMR. Start from the number of the peaks. How many number of the peaks we have? We have 4 peaks. Can you see that? It's actually should split it. It's 1, 2, 3, and 4. That's why it's shown the kind of magnified. So enlarged peaks here. There are 4 peaks.
Oh.
Telling you what? as a 4-carbon environment. But you have to think about the formula here. The formula is given as C5. There are 5 carbons, but we only have 4.
So
That means that 2 of the carbons must be the same, or they must have the same carbon environment. Which indicates there's a possible of the methyl. We can have a methyl in here. Okay, what else? Now, time to use your data sheets provided here. You look for the most shifted the peak. That peak is located at 170 here. So use your data sheet. You can see the peak at 170 ppm. Tells you about what? Use your data sheet. It says it's either be telling you esters or the alcohol. But do we have alcohol? So it can't be the alcohol. It must be the esters. Confirm that the functional group must be the esters. Okay, that's the information we can get from the CNMR. Everyone happy?
Yes.
Now move on to the then HNMR here. 1 HNMR. See what we got here. So start with a number of the peaks. How many peaks we have? We have 1. There are if you're confused about the peaks here for HNMR, it's given. There are 3 peaks. Data from HNMR here. There are 3 peaks. Telling you what? There are 3 hydrogen environment. Okay? Now, it's interesting that we are given some chemical shift. Let's use the chemical shift here. Chemical shift is 5. So only the one having a 5 is somewhere in the alcohol and ester, which is this. This is how you use the data sheets first of all. Or you can think about the relative peak area. For start from 6 over here. Having the relative peak area 6 means what? There are 6 hydrogen having the same hydrogen environment. For those 6, the splitting pattern is doublet. Okay? Remember that the splitting pattern is doublet. So we have 2 CH3s here like this, okay? Having a 1 carbon with the hydrogen. Does it make sense at all? Because it has a 6, 1, 2, 3, 4, 5, 6 hydrogen with the from the relative peak area. Having a doublet means from them they have 1 hydrogen in between from the doublet. Okay, that's what the first information we can get. The second information we have, the relative peak area is 3. Okay, having a 3 carbons, 3 hydrogens. You can think about CH3 here. Okay, having a singlet. Oh, having a singlet. That's interesting. Could it be? Most likely related to O here. So, or you can use the pattern chemical shift 2.0 is somewhere in here. It's either be this one or this one from the ester. It's giving you that the structure is then CO, carbon with the oxygen. Oh, sorry, single oxygen. Okay, and then we have a CH3. Okay, now it's kind of giving us the structure of the ester now. To finish that, the ester structure, it would be ester here, carbonyl. Okay, and make filling up, that's 2 hydrogens. There'll be 3 hydrogens. Now, last one, we have a septet that has a chemical shift of the 5.0. The 5.0 is which is here, the last section here, CH2. Okay, and it also has this septet. So, and with the relative peak area. So this is representing this one over here. Having a 6 neighborhood hydrogens, having a septet. Okay, having a 1 relative peak area.
Can you explain that? Ester part again, right side.
So it would look like this. We have a 1 ester. Think about ester structure. Okay. this is ester structure, ester functional group. First of all, here we have a 4-carbon environment with the 5 carbons. So to make it possible, we need to have something with the methyls. The possible methyl, as you guys can kind of predict it here, started from the CH3. So started from this one here again, it's the chemical shift 2.0. That's giving you CO and CH3. This is confirmed then. Okay. Now the next section we have carbon. Show that carbon, 3 carbons here. Okay, with the 1 methyl attached on the top. Is that similar to what you have?
Yes.
Yes.
So do you also drink?
Yeah. I'll buy you a drink.
When we're 18, on the boat, together.
Milk tea, right now.
Not now. Okay. That is the structure of the compound using that. Yeah,
Is that the same?
They're the same.
Oh yeah, they
Okay? This is how you do.
We did it. Teamwork.
Good job. But for your 7 marker, the reason why I ask you to do the planning is after you do the kind of dot point planning here, you just need to connect and make it into sentences. You just write it down. This is why you need to write sometimes 2 to 3 pages.
Oh, just on this.
Yeah, 7 marker.
1 page for the planning.
Like 1 page for the rough planning, like a 1 page. Like you don't have to show the planning. You can just go like planning on any other area here. So this might be that, and just connect all the informations, and then finalize that why using the H and M as the pick, the key that to find out why is that this structure given over here. Does it make sense? Okay, this is what you would get in the HSC. Now have a look at the 2019 HSC question 2. That's what we had.
What page?
Question 3, page 185. The following data were obtained from the organic compounds containing carbon, hydrogen, and oxygen. Compound is colorless liquid that reacts with sodium carbon powder to produce bubbles. What does that mean? It must be the It must be the could be the carboxylic acid. Okay, shall we confirm that from the infrared?
Yes.
Yeah, it is carboxylic acid. How do you know?
OH and CWA.
Yes, we can see both of the carbonyl and hydroxyl. Very good. And then this is what you need to think before you write something in here. Jomin, what else?
Mass spectrum.
We have mass spectrum here. What information can we get from the mass spectrum? 74 is the molar mass of the carboxylic acid.
75?
That would be 74. We take that. Yeah, 75 would be isotopic. Yeah. 74 is a mass number here. Now, can you guys like now know how to collect the required information for each? Press tick. We got the mass spectrum 74. Mass numbers give it.
This seal will be hot. Because of the isotope, right? The ring.
What did I just said about this functional group?
It is a carboxylic acid.
Yeah.
But
1, 2, 3.
Yeah.
it's kind of like Cl or Br included.
Does it really?
Because of the length of the mass.
What length? What length? If you have a Cl or Br, you won't get the one difference of the 1. You get difference of 2. So don't worry about it. Now CNMR tells you what? Jeremy, CNMR tells you what?
3, 2, 3.
3 what?
Hydrogen environment.
CNMR.
No.
So carbon 3 carbon environment, and from the shift. From the shift. Use your data sheets, guys. From the shift, the most shifted data pick here. What can you tell?
Esters or acid.
It's acid or acid, but it's kind of confirmed the acid again. That's what you need to write. It's confirmed it's an acid. Yeah, it's confirmed it's an acid. Then time to use the H and MR given over here.
Propanoic acid.
Was that big propanoic acid? Do you reckon? Oh. Why? From the H and MR, what can you tell?
The from the first spike, the relative peak area is 3. So that means it has 3
Mm-hmm.
carbons, right? And the
3 hydrogens, you mean?
3 hydrogens. And in the neighboring
2 hydrogens,
carbon, it will
yep.
have 2.
Okay, and
that The second one, the one.
So
next to
what
it
is this?
kinda-
This is triplet.
Yeah, triplet.
And what is this? It's a quartet.
Oh, yeah.
So those two are
That's
kind of
what?
respective.
That's one hydrogen with singlet. So what information can we get from there is we have three hydrogens, which has the neighbor of the two from the triplet. There are two neighborhoods. Okay, we have a two hydrogen having the three hydrogen. So these are basically talking about both over here. Okay, then we have carboxylic acid with the OH. So this will be propanoic acid. Check with the mass number here again. What is the mass number? 12 times that 1, 2, 3 plus 1, 2, 3, 4, 5, 6. 6 times the 1.008 plus the 1, 2 oxygen. 2 times 16. Then you get what?
74.
74. Confirmed.
Is it good to show the calculation at the end?
You got to show the calculation at the end because it's got to relate it to like that here. See? A. What is the structure formula of the compound? Justify your answer with the reference to information given the reactivity to the at least 3 of the provided spectra. 5 marks. Too difficult? Untouchable?
Yes.
This should be the easiest question that you will get in your HSC. Something that you can predict, something that you can prepare. So this is what I mean by it's actually easier than module 5 and 6. You can't predict what you will get in module 5 and 6. I can't predict it. Module 7 and 8, I know what will be in your HSN trials. It's so easy. No, not from the polymers. Polymer maybe or may not be. You will definitely get a question about physical property, intermolecular
What's the
forces.
chance of getting like polymers and
Saponifications?
saponification?
Pretty high for this year.
Oh, because it hasn't come out the last couple of years.
Not yet. Not many.
Fucking hell. But there
Wait,
is
what
a
did you ask?
What's the chance of saponification and polymers coming out?
Pretty
Oh,
high.
It's disgusting.
So there is a chance that like in a HSC, in like a random HSC, a given HSC, that saponification
Random HSC. give you that.
might not come out.
That really depends who's writing that paper again too. But trials again, like because every trials are based on the previous year's HSC, and yeah. But this is the guys. This is the question type of question that you can do. Depth study. If you got a depth study for module 8, most likely this one. I told you, school will not sometimes teach you how to analyze those IR, NMR, all their mass spectrometry, and just ask you to do this. I know if there are 3 schools from my students, they did that depth study for this one. For those who learned that prior to the depth study, they found that the depth study was the easiest out of the whole year 12 because they know how to do it. They just need to write the answer like a 7-marker questions. So they finished that in a day or 2. But think about those who didn't learn that beforehand. They needed to study for NMR, mass spectrometry, and everything by themselves. There's a chance you can get a questions related to UV visible UV spectrometry this year because we have UV absorption there. We're going to talk about the UV later on. I'm going to focus more on this one first and then move on to UV later. But UV spectrometry is also very similar to the IR, basically. We have the very specific lambda max and using that too. But that's a bit later on, we're going to talk about it. Okay? First, I want you to master those IR, HNMR, CNMR, and mass spectrometry, and some chemical tests. That's the first step. Master those. Master as in like, you know what you're looking for. You know what information you can get. Especially for the HNMR. Can you guys see like now, combining all that different information, you are able to get what the structure could be. So question B, explain why the chemistry uses more than one spectroscopic techniques to identify an organic compound. Use 2 spectroscopic techniques to support your answer. Jongmin, why do we need to use more than 2? Sometimes more than 2. More than 1.
Because you can't get enough information on just one tooth.
For example.
For example, if you look at the infrared spectrum, you can identify the functional group, but how are you gonna know, like
Exactly. Good. So that what do you recommend use with the infrared then?
Infrared and CNMR spectrum and HNMR spectrum.
Or one of the NMRs?
One.
One of the NMRs most likely, and how to go for the mass because we probably didn't know about the mass of this yet.
You
Or
have to know mass. just like we use it for confirming?
If you don't have the mass in here, because you're not given the actual the carbon and hydrogen here, without knowing the mass, you could have actually various structures of that too, possibly.
So you just say like, if you just use infrared spectrum, like you're limited to not having a molar mass.
Mm-hmm. Molar mass or the exact specific structure of the compounds, so that it is all the HNMR or NMR data is required to get specific structure. So that because we can get the number of the hydrogen and carbon environment as well as the possible chemical shifts. So you just need to narrate that, what information you can get from each of the data given over here. Okay, easy question. Easy, as in like you know what's in there, you know how to answer that. You just need to memorize. You just need to use a little bit of your brain to work it out, just like solving a puzzle. Now, another thing that I said this is easy is, even though you get it wrong with the structure, partial marks, as long as you have a supporting your answer in the good reasoning. So for this 5-marker question, yes, even though you got a wrong structure, you can get 4 or 3 out of 5.
You can get 3 out of 3.
Yeah, so you can get like what? 6 out of like whole 9 marker. Is it a 9 marker?
8.
8 marker. You get a 6 out of 8, which is pretty decent. I would call this an easy question. I really say this is an easy question because you can get a high chance to get an 8 marker. So Band 6 students will never lose a mark for these type of questions. Not even a single mark. They lose a mark from really complicated, some more complex calculations probably by the mistakes. Multiple choice maybe, and things happen. Multiple choice last year was quite hectic. It was quite complicated. So yeah, so you can lose a mark because of that, but you can't lose because of from here. You shouldn't lose any single mark. Make sure you practice that. You are given the sample answer from the samples that I gave you last week. What I mean is, from the sample question, you guys all have that sample question? Yep. You have that, the sample data analysis here. This giving you sample answer provided on the page 10 and 11. You need to write as much as here. Told you, 3 pages. Chemical infrared, you need to write like infrared section. You need to write as this. Mass spectra, you need to write as this. For the carbon 30, you need to write as much as here. Protein NMR, you need to write as much as here.
So for question like A that we just did, we actually need to write.
Oh, don't rely on the space on there. Don't rely. That's a minimum. And minimum means you get a minimum mark. This is why you always be provided those extra answer sheets for those. Okay, guys. Now I gave these samples for a reason. You get the sample A to Z. Sample A to Z here. And each of those have the very specific, all the data is given. If you're lucky, you may get one of these in your trials.
What else could they give you?
Is this from like NASA?
This is from NASA.
I don't even know if we're going to get up too much of
Good chance.
If you're up to like
Oh, are you sure? You get up